question 6.1, which is area between curves. So the idea behind this section is that we're looking for the area between these two curves here. And what we're going to do is we're going to break this up into n number of rectangles. And we know the formula for a rectangle is base times height. And here's your base, it's delta x. And here's the height of that rectangle. It's the top boundary function minus the bottom boundary function. And that's how you figure out what the height is. So you come up with this Riemann sum, which can then be written as a integral. And the conditions are that the curves f and g must be continuous, and that f must be above or greater than or equal to g within that interval, a to b. So let's take a look at our first example. So first thing you always want to do is sketch the functions. So if you sketch these functions, it'll look something like this. It doesn't have to be a perfect graph, just a rough estimate. So let's graph one of these. I'll graph this one first, the y equals 2x. That's just going to be a line through the origin with slope 2. Doesn't have to be perfect. And then the other one's going to be a parabola, and that's going to look something like, let's see, it's going to look something like this. All right. And there's 2 points of intersection, one at the origin. And the way you find the points of intersection is you have to set these two functions equal to each other. That's how you find the points of intersection. So x squared minus 4x equals 2x. That's because they're both equal to y. That's why you're allowed to set them equal to each other. So if you solve for the zeros, you're going to get the points of intersection, which are 0 and 6. So that tells us our limits of integration. All right. And as you can see, the top function is y equals 2x, and the bottom boundary function is x squared minus 4x. So that's going to allow us to write our integral. So the area is going to be from 0 to 6, f being 2x, and then g being x squared minus 4x, and all of that with respect to x. All right, so here's our little rectangle, and this is what we need to integrate now. So let's go ahead and integrate. Let's see what we get here. So after simplifying this, you should get, it's going to be all right, and then taking the antiderivative, that's going to be negative 1/3 x cubed. That's going to be 3x squared. All right, and we're going from 0 to 6. So if you plug in 6, that's going to be 6 to the 3rd, which is 216 over 3 plus 36 times 3, 108, minus 0, because when you plug in the lower, they both are going to cancel out. So now we just need a common denominator to combine these two fractions, which is 3. I think 216 divided by 3 can be simplified. That's actually going to be 72. Negative 72 plus 108 is going to be 36. And that is our final answer. So that is the area of the region that's bounded by those two curves. Let's take a look at another example. This one, same thing. You want to start off by graphing, and remember, it doesn't have to be perfect, your graphs. It's just a sketch is good enough. We know what x cubed looks like. Hopefully you know it. It looks like something like this. It's a cubic function. And then y equals x is just a straight, is a line that goes right through the origin. I should probably exaggerate the graph a little just so that we can get a better sketch. Okay, that was not the best looking graph. Let me try that one more time. It's a little better. So you can also use symmetry to your advantage. As you can tell, this region is equal to this region. So that means we only have to calculate one of the regions and then multiply by 2. So that's because of the symmetry of these two sides. So you always want to use symmetry to your advantage. So let's find the points of intersection by setting these two functions equal to each other. Because they're both equal to y, subtract x over, factor out an x, and factor once more the difference of two squares. And there you have your points of intersection. So this would be -1, this would be 0, and this would be 1. But like we mentioned earlier, we're just going to calculate this region and then multiply by 2 because of the symmetry. So let's write our integral. The area is going to be equal to 2 times 0 to 1 instead of -1 to 1. And the function that's on above would be this one, which is a line, which is x minus, and the function below would be the x cubed function. And this is all with respect to x. So now we can go ahead and integrate. That's going to be 2 times 1/2 x squared minus 1/4 x to the 4th. And we're going from 0 to 1. So that's going to be 1/2 minus 1/4 times 2, which is 2 times 1/4, which is 1/2. So that should do it for that one. Okay, so that is the correct answer. So let's move on to the last example in this section. So let's start off with graphing or sketching the graph of these two functions. All right, so notice that it's x in terms of y, and they're both square functions. So if you graph these, you can use a graphing calculator. You can use Desmos.com if you like. If you haven't heard of Desmos, it's a very good website, Desmos.com, and it will allow you to graph these functions if you don't have a graphing calculator. All right, so these are both going to look like this. One of them is going to be at the origin. The vertex will be at the origin. The other one would look like also like a parabola, more like that. So let's find the points of intersection now, which is one up here, one down here. All right, and because they're both equal to x, that means we can set the two functions equal to each other. 2y squared equals 4 plus y squared. Subtracting y squared gives us, and subtracting the 4 over. And as you can see, this is going to be plus or minus 2 for our points of intersection. But those are the y coordinates. So y is going to be positive 2 up here and negative 2 down here. So this time it makes more sense to integrate with respect to y because our rectangles are going to be sideways. As you can see, it's easier to integrate top, bottom, as opposed to left, right. So, and it makes sense because you can see that the functions are x in terms of y as opposed to y in terms of x. So our integral will look slightly different now. And once again, you can use symmetry to your advantage. You don't have to go from -2 to +2. You can just go from 0 to 2 because this is equal to this. So let's do that. Let's multiply by 2. We'll go from 0 to 2. And this time our top function is going to be this, and our lower function is going to be this. So our top function is going to be this one, and our lower function is going to be that one, or our bottom function. So it's this minus this. So let's write that out. 4 plus y squared minus 2y squared. With respect to y this time, as you can see, we're with respect to y this time, not x. So simplifying this gives us and now integrating will give us and then this will become 2 times -8/3 plus 8 minus 0 again. All right, and I'm running out of room, so I'm just going to continue up here. So that's going to be, this is going to be a 1. So that's going to be times 3. That's going to be 24 minus 8 is 16 thirds. So it's going to be 2 times 16 thirds, which is 32/3. And that should do it. That is our final answer. And that concludes this section.